Good morning, ladies and gentlemen. Thank you very much for attending the webinar. Today is a beautiful day on December 5th, 2018, and only 20 days until Christmas. Hope you all have got your Christmas shopping done. Anyway, I'm excited to present today a webinar on cavitation modeling with AFT Impulse. And so I want to let you all know that this webinar is being recorded. That way, if you're listening in live, you'll be sent a link to where you can watch it again later, or you could send it to your colleagues. If you are listening in later, not live, well, you're obviously listening to the webinar. I did attach my presentation to the webinar. That way you have access to the slides. I also wanted to attach the model files that I'll be demonstrating today, but unfortunately, the GoToMeeting does not allow zip folders to be able to be attached. So if you email me personally, whether you're listening live or listening later, email me at benkeiser@aft.com. That's benkeiser@aft.com. And I'll be more than happy to send you my slides as well as the model files that I'll be demonstrating today. That way, if you have AFT Impulse, you'll be able to work with it on your own. All right, so I'm going to go ahead and get started today, and we're going to be talking about cavitation. So here's the million-dollar question. You have a pressure surge event due to a sudden valve closure, and you have a sustained high pressure in that area. And right here, this is a plot of the pressure and the vapor volume at a inlet of a valve, which is at the end of a pipeline, and you're slamming that valve shut. Well, you have all these pressure spikes there that are the pressure response at the valve over time due to the valve closure. And so the question is, with all those pressure spikes, are those pressure spikes real? i.e., when you go to design your piping system, are you having to design your piping system for 900 psia, or would it be around 700 psia based upon the valve closure? If you have pressure spikes way out here, are those realistic or not? And so that is what we are going to look at today, is techniques that you would use with AFT Impulse on how to evaluate your cavitating results. Now, why is this important? Well, if you are a fan of the Matrix franchise, would you like to take the blue pill or the red pill? You take the blue pill, the story ends, you wake up in your bed and believe whatever you want to believe. If you take the red pill, you stay in Wonderland and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth. I thought that this was a very good introduction to the webinar because interpreting waterhammer results is very much of an art as it is a science. As engineers, we like to be able to put an answer inside of a box and say, the value is this, or the flow rate is exactly that. And with waterhammer, it's very difficult to put a single box around an answer. It just doesn't exist. There's a lot of gray area involved when you're doing a waterhammer analysis. The answers are not straight black and white, especially when you have cavitation. So ultimately, you as the engineer needs to decide if your results are realistic or not. And that's why I'm going to show you various techniques that you can employ to make those determinations. Again, i.e., does your system need to be able to withstand a maximum pressure of 750 psi or maybe 850 psi? So here's what we're going to talk about in today's webinar. I'm going to give you an introduction to what cavitation is, the cavitation models that are available and how they're slightly different, and we'll talk about the related uncertainties to cavitation modeling. I'm also going to show you a few comparisons of the cavitation model results compared to actual measured data. and I'll show you where you can actually find that yourself in AFT Impulse, which I'm actually going to show you right now. If you were to install AFT Impulse, including the demo version, if you went to where it was installed, which is typically on the C drive, in the AFT products folder, and then the AFT Impulse, there's this verification folder right here. And if you open up the verification folder, it contains a verification help file that you can open up, as well as a, I guess I'm probably not, you may not be able to show my screen. Let me see, what am I? Oh, okay, good. You are seeing it. Sometimes PowerPoint plays tricks on me when I'm giving presentations and I'm not sure what you're able to see or not see. And so, as you can see, there's a whole bunch of model files. Those are models in Impulse that we've built of several different published examples and published technical papers and textbook examples, and we do a results comparison. And so that's what helps validate if the answers in Impulse are what you would expect. And in the help file here, if you open this up, it contains several verification cases that involve cavitation, such as case number 4 right here. As you can see, this involves cavitation, and you can see other results. So I'm going to go over a few of these slides after I finish discussing the slight differences between the two cavitation models available. And so that's where that help file is located. Then we'll talk about some techniques and guidance on how to evaluate cavitating results, and I'll go over some examples. There are some important Impulse webinars and technical papers that I want to highlight for you all. If you have not had a chance to already watch the Impulse webinars that we did back in October and November of 2018, so just a couple months ago, you can access those webinars in our webinar library right on our website. They are free for your viewing, and you'll be able to learn a lot of information. The webinars I would recommend watching are the AFT Impulse Introduction. In that webinar, I talk about an overview of AFT Impulse and how it uses the method of characteristics to solve the system of transient pressures and flow rates throughout the piping network. I did another webinar on mitigating surge issues, and that is how you can use surge suppression equipment in order to mitigate surge events. Ronaldo Pinto did a webinar on pulsation control using the AFT Impulse PFA module, and then I did another webinar a couple weeks ago on essentially how to evaluate your waterhammer results effectively. So this is a really good one where I show a lot of the different graphing capabilities and how to look at your results in an efficient manner. So if you haven't had a chance to watch those webinars, be sure to do so. They are somewhat of a prerequisite to today's webinar, because today I'm not going to be talking about the basics like what pipe sectioning is or what time steps are. I'm assuming that you're going to view these resources later to learn what those topics mean. So today I'm focusing really just on cavitation. There's a few technical papers on our website. There's one that talks about when the Joukowsky equation does not predict the maximum waterhammer pressures. So if you go to our website, aft.com, under the Learning Center, you can go to technical papers, and there are 3 new technical papers that we've recently published. It's these 3 right here. And these 2 webinars are key because that's a 2-part technical paper series, which gives really good guidance on how to evaluate cavitation. So I'm touching on the very basics today. I'm introducing you to what cavitation is and to give you some ideas on how to understand it better when you're running your impulse analysis. If you read those 2 technical papers, it'll give you a lot more guidance on what to do when you have cavitation. And again, it's not going to give you a way to be able to box in a single answer. You're going to have to make a judgment on what you believe is real or is not real. and how to design your system in accordance with that. And so these will give you some good rules of thumb to be able to do that. I also have provided direct links to each of those technical papers right here in my presentation, so you can access those later. Also, in the main AFT Impulse help file, we have restructured it and added a lot of brand new content with AFT Impulse version 7, which just came out a couple of weeks ago. And so we've restructured the format of the articles inside the help file. And there's an important one that I want you to read. It's in the topic here, or the section, Interpreting Transient Results. And there's a really good topic on interpreting cavitation predictions. And so this is brand new content where it was essentially summarized from those two technical papers. And so this will provide you some good guidance on what to do in cavitation situations as well. Again, my webinar today is going to be much more simplified fashion from what you'll see here. This will give you more detail and guidance. Lastly, there are a lot of excellent video tutorials for AFT Impulse on our website, and these videos here on the left-hand side are very basic videos that will help get you up to speed with the basics of using the Impulse software, so I'd recommend reading those. These talk about how to model different types of transients, and then these videos over here were actually new feature videos for Impulse 6, but the key thing is they highlight how to use the graphing capabilities. So if you haven't had a chance to watch those, be sure that you do so, especially the video on sectioning. All right, so in order to kick things off here, I want to show a quick video that really does an excellent job at highlighting cavitation. So let me pull that up here. When you get the presentation, you'll be able to watch the video as well. And I just got to make sure that I switch over to using the correct audio. Let's see. Hang on a sec. Hang on a sec here with me. There we go.
Your partner for Vast Technology. The water hammer effect. What is really happening during water hammer effect? The following pictures are taken with a high-speed camera with 1,000 frames per second. We focus on that forces that are generated when water is punching on the valve. Water hammer effect is activated by fast closing of a valve. Forces during water hammer effect. In proper speed, these effects are not visible to the naked eye. The pictures of the high-speed camera show how a steam vacuum is generated, how the water column is pulled back and punching on the valve. Consequences of water hammer effect. In slow motion, you see how water spray squirts out of the flange gasket area. The studs are stretched, and at the same time the whole construction is spoiled with a deflection of 50 millimeters. The forces. Vacuum is generated and pulls the water column back with a vacuum pressure of 0.1 to 0.2 bar. The measured distance for the backflow is 30 centimeters. Water covers this distance within 64 frames, that means in 64 milliseconds. 30 centimeters comply 4.7 meters per second or 17 kilometers per hour. This is comparable to the speed of a cyclist. Now steam bubbles are decomposed and deceleration begins. For comparison, a pursuit plane reaches 10 G at most. In an accident, deceleration is 50 G at most. Within 8 milliseconds, the speed of the water is dropping to zero. In this time, you cannot see any vacuum bubbles. That corresponds to an acceleration of 586 meters per square second, or 59.7 G. During the deceleration, there is a force of 29,300 Newton on the surface of 50 square centimeters. This is a pressure of 58.6 bar. The actual load on the disc is as high as if a heavy truck weighing 3 tons would rest on it.
All right, so that's a really good video that we show as one of the videos in our AFT Impulse training seminars to illustrate what cavitation is. And the question is, how do you go about modeling that? And it's tricky. And so there's a lot of interpretation that you need to be able to do and understand. So let's get into some of the details here. There are two methods for evaluating cavitation in AFT Impulse. There's the discrete vapor cavity model and the discrete gas cavity model. If you open up the transient control window from the analysis menu, this is where you can pick which cavitation model that you are going to be using. And I'm not going to spend too much on these basic slides here. The main thing is that when you're using the discrete vapor cavity model, it's been there in Impulse for a long time, works really well for very short-lived minor cavitation spikes. And so it has the potential to very quickly produce non-realistic results when you have lots of cavitation going on. The discrete gas cavity model does a better job and has more stable results than the discrete vapor cavity model, especially when you start looking at the second and third and later pressure spikes into your model. But the same thing, though, is if you start to cavitate a lot and you're using the discrete gas cavity model, it still has the possibility of predicting non-realistic spikes after you've been cavitating for a long time. And if you have cavitation that's excessive with using the gas cavity model, sometimes you might have some difficulties converging in the transient solver. Also, it can potentially increase your runtime a little bit. So it's a little bit more accurate, but those are some drawbacks that you are not drawbacks. There are some challenges that you might run into. So be aware of that. Here's what the discrete vapor cavity model is doing. When it's calculating the new transient pressures and flow rates at each time step, what would happen is if the new pressure, the new pipe station, this is an intermediate pipe station right here inside of a pipe. If that pressure drops to the vapor pressure, then we're going to have cavity formation. And the key thing is, if you have that cavity formation in Impulse, the pressure is going to be fixed at vapor pressure. So it's a pseudo pressure boundary at that time. The key thing that I want to point out here is when you have vapor pressure, your flow rate no longer balances at that computation section in your pipe. That's why we have the parameters mass flow rate upstream and mass flow rate downstream. That's because they will not balance across a vapor cavity in that fashion. If you want to see how this equation is derived, you can consult the help file, and that'll go through the whole method of characteristics for you. But the key thing is, when you're using the discrete vapor cavity model, once you start cavitating, your pressure is fixed at vapor pressure, and your flow will not bounce across that vapor cavity there. The discrete gas cavity model does a bit better at handling cavitation, and the reason why is because it can treat the cavity pressure as a variable. So with the way that the gas cavity model works, instead of just fixing the pressure at the vapor pressure, the pressure can actually be different than vapor pressure inside a cavity when you're using the DGCM model. And so I'm not going to go over all these bullet points here. You can read them later at your own leisure, and this will talk about how the discrete gas cavity model is different. The key thing is when you're cavitating in real circumstances, the wave speed of the fluid will change. Impulse is going to assume a constant wave speed. That's why the mathematical models behind these two cavitation models are a bit limited due to the assumptions of that constant wave speed. But the key aspect of the DGCM is that it's able to handle a variable wave speed to kind of do a mock variable wave speed without actually changing the wave speed. So that's one of the key differences. These are some more bullet points here on the discrete gas cavity model, and I'll let you read those on your own. But here's the two cavitation models compared with published data, and these are examples that come right out of our verification help file. And so this first one is of a sudden valve closure. I'm going to be showing a similar example to this today. And so as you can see here, we have the red line, which is the published data, the blue line, which is a discrete vapor cavity model, green line is discrete gas cavity model. And this is looking at the pressure right at the inlet of the valve when that valve slams shut. So as the valve slams shut, the pressure increases. This pressure can be verified with or compared to the maximum theoretical pressure equation, the Joukowsky equation. And then as that pressure wave reflects from the valve back up to the reservoir, you'll see how the pressure drops. And when it drops down to vapor pressure. Well, after that vapor pressure is collapsed, it reduces or it results in a large pressure spike. And that large pressure spike actually gets up to be significantly high. Now, if you look at this and follow the red line, you can see that it gets up pretty high. Both the green line and the blue line are following that trend really well. One thing when you're evaluating cavitation is you're never going to be seeing the exact same results every single time. So if you have data at 90 feet right there or 90 meters, it's very likely that you'll see slightly different results in the cavitation models. What you're looking at is the overall magnitudes. How closely in magnitude are the cavitation models predicting what was measured right here? And as you can see, they're very close, but the blue line for the discrete vapor cavity model does predict slightly higher pressures in these first few pressure spikes. After that, it drops, the pressure drops again, and you start to cavitate more, and then you have more pressure spikes. Well, as you can see in here, as you read the bullet points, the discrete vapor cavity model very quickly starts to overpredict higher pressure spikes when cavitation becomes excessive. And so this is why when we're providing guidance on how to evaluate cavitation, it's the first one or two pressure spikes, maybe three, that are going to be the most reliable when you start cavitating, especially with the DVCM. As you look here, the discrete gas cavity model is much, much more in line with the published data. And then as you go out later in time, your discrete gas cavity model follows the published data very well as compared to where the discrete vapor cavity model dramatically overshoots those values. And so again, this is where you have to really look at things carefully to figure out what's going on. Excuse me. Okay, Let me go on to the next slide here. This is the same piping system, but instead of plotting the pressure at the outlet of the valve, it's plotting the pressure at this interior pipe station. So maybe that's 200 feet into the pipe, perhaps. Well, you see the same pressure surge, which is slightly delayed, but then you start to have cavitation at this point, and you start to see the pressure response due to cavitation. Again, the gas cavity model is following the measured data a lot better than the discrete vapor cavity model. Not only do you pay attention to what the overall magnitudes are, for the pressure spikes, you also want to pay attention to the timing and location. So if you see pressure spikes starting to happen in a certain area with one particular cavitation model, if you look at the different cavitation model, you should see spikes around the similar area and the similar time frame. And if the magnitude of those pressure spikes are relatively close, then that can serve as validation that maybe those are a bit more realistic. Again, you're needing to focus on the overall trends themselves when you're modeling cavitation, not the exact values themselves. This is just a different example here, again, right out of our verification help file. Instead of doing a valve closure, it's a simulated pump transient. So essentially, we're dropping the pressure at a pump to simulate a pump trip. And so this is the pressure response that you would see, which causes cavitation. And again, you can see how the discrete gas cavity model is doing a much better job following the measured data than the vapor cavity model. Just a different area of that same system for the pump transient. So what I want to do here is I want to jump back in to the single valve closure that I demonstrated with the AFT Impulse introduction webinar back in October. So if you watched this, if you watched the webinar from the beginning of October, which you can find on our webinar library on an introduction to AFT Impulse, I talk about this example in a lot more detail. But the key thing in that example is I ignored cavitation. In this case, we're not going to ignore cavitation. So what we have is a upstream reservoir and a discharge valve that's just discharging right into the atmosphere. And the transient is that this valve is closing instantaneously, and we're going to allow cavitation to be modeled, and we're going to take a look at the results. So let me go ahead and jump into Impulse now. So here's my Impulse model. As you can see, I have done a whole set of different scenarios in the scenario manager. So here's my process. I started off with this base scenario, and I built my model, I defined my fluid properties, etc., etc. I specified a instantaneous valve closure, which I caused the valve to close in in 1 millisecond. And then I have sub-scenarios. So I have a parent case, which uses the discrete vapor cavity model, and then I use 10, 20, and 30 pipe sections in the pipe. And then I have the gas cavity model, and I use it again, 10, 20, and 30 sections. So when I was building this model here, this makes very good use of the scenario manager, because I just defined this scenario once and with the vapor cavity model, and I changed the sectioning in each of these scenarios. What I could then do was right-click on this parent scenario, and I cloned it with children. When I did that, it created the scenario here, which I renamed. I called it the gas cavity model. So for the DGCM scenario, I went into the transient control, and I chose the gas cavity model for my transient cavitation that I'm using. The sectioning was already set up in these scenarios. So when I make the change in this parent for the discrete gas cavity model, that change propagates down to each of these children. So I only need to make the change once. After that, I did another cloning operation where I took this closure time scenario and I cloned everything inside of it. And when I did that, I created my 1 second closure case. All I needed to do in this 1 second closure case was change the closure time for the valve, and that changed everything down here in my scenario. So I only needed to make the change once. And then I closed things one more time and I did a 2 second closure. So what I did was, after all those scenarios I created, I went to File and then Start Batch Run. And essentially, I added all the different scenarios to be run in a batch mode. That way, it would be very efficient. And once I was done running them, I would come back and I would look at the results. So let's take a look at the results for the scenario where the valve is closing in 1 millisecond. As you can see, it's closing in 1 millisecond here. And I'm using the discrete vapor cavity model, and I'm using 10 sections in my pipe. My pipe is 2,000 feet long. I'm using 10 sections, and so that means that each segment is 200 feet long. And so these are the results for that analysis. If you look at the results here for the output, well, the good news is you don't see any warning messages. So just because you don't see any warning messages does not mean that your results are good. You can have some significantly problematic results without having any warning messages at all. Moral of the story is you can't just assume that because this is blank that your results are correct, and you can't just look at these results and be done with it. You see that you have a maximum pressure spike of almost 900 psi, but this gives you no indication as to what's going on at the time in which it occurs in your system. You have to look at things much deeper. What is an indication that you have cavitation when you do not have any warning messages telling you that there's cavitation? Well, your first thing that you can do is, if you scroll over here, there's a parameter for maximum vapor volume. If this is non-zero, then that implies that you've got cavitation at some point in your system. But again, this is not telling you the whole story. So what you need to do is you need to look at things at a deeper level. So let's go to the graph results, and what I'm going to do is I'm going to plot the transient pressure at the outlet of the pipe, which is the same thing as the valve inlet. So I added my outlet of pipe P1, that's my valve inlet pressure, and I plotted both the pressure as well as the vapor volume. So I'm doing here what's called a stacked graph. I talked about this in my webinar that I did last month in the middle of November. So you can see those graphing capabilities there. So when I plotted this, this is the transient response that you see. Here's your sudden valve closure. This pressure of about 660 psia would compare with the Joukowsky equation. But then once you drop to vapor pressure, you start to have a vapor cavity form. So if you plot the vapor volume, this makes it really easy to see what's going on. When you drop down to vapor pressure during this time frame, you should see a vapor bubble form, and then once that vapor bubble collapses, you'll see an associated pressure spike. It drops the vapor pressure again, and then there's another vapor bubble. Once it collapses, you have another pressure spike. And then when it drops for a significant amount of time, you have a really large pressure spike there. And so that's the transient response that you can see. And the question is this pressure realistic or not? Do you need to design your system for, almost 900 psi? Well, it's hard to say by simply looking at this. One of the rules of thumb is to analyze what your relative vapor volumes are. When Impulse is doing the method of characteristics, it has to break your pipes up into sections. And so here we know that our pipe is 2,000 feet long, and we are putting 10 sections in that pipe. From that information, based upon a 200-foot long segment, you can calculate what the volume of that segment is. What you would do is you would compare that segment volume of your section with the vapor volume that you see here. If the vapor volume that you see here is 10% or more of what your section volume is, then the ability for the cavitation models to accurately predict cavitation will become less reliable. Again, there's a lot of things that you need to look at, not just that rule of thumb. It's, how about this volume? Is that okay? Or is that okay? You have to look at all the things together. Well, what you're going to be able to do in the next maintenance release of AFT Impulse 7 is what I did here. I created a graph list manager item. So this is all Impulse 6 stuff. So this is stuff that you are already able to do. So all I do is just double click on that graph, and it regenerates my pressure in one shot. The reason why that's extremely useful is when I go and look at any of the results in these other scenarios, I don't have to reset those parameters every time. All I need to do is create that graph list item and double click on it, and then it regenerates my graph on the spot for me. So the next maintenance release in AFT Impulse 7 will allow you to use the Excel Export Manager, which is a new feature where you can choose to automatically send results to an Excel spreadsheet. So what you can do is you can add a new row. Eventually what you'll be able to do is you'll be able to choose a graph as the export type, and then soon for the source you're going to see a transient pipe and transient junction source. And so once those new sources are available, what you'll be able to do is essentially automatically you'll be able to spit out the XY data that you would be able to see right here into a spreadsheet. Now, when I was preparing for this webinar, I had to do it manually because that feature is going to be in the next maintenance release. So what I did was I clicked on this button right here to copy the XY data, and I pasted it into my spreadsheet here. So I have several tabs along the bottom with the different scenarios that I'm modeling. So the first scenario that I'm modeling is the discrete vapor cavity results. So this is a discrete vapor cavity model for the 1 millisecond closure. And I look at using 10 sections, 20 sections, and 30 sections. The reason why I'm using different sectioning is because if you change the sectioning, your results should still be relatively similar. And so what I'm looking at here is if I show just one graph at a time, this is the data that I just plotted for you. So this is based upon using 10 sections in that pipe. If I do 20 sections, what I'm looking for is how do the trending results compare with the two types of sectioning. So as you can see here, if you look at the blue line in this area, you see some large pressures that spike when that cavity collapses in this region. Well, when using the 20 section scenario, I have a very similar transient response. So I have similar results that are around the same magnitude upon the pressure spike. The timing is similar in that area. Also, the area where this is happening at the valve inlet is very similar. So if you see how things are matching up together like this, and if they're comparable, then this might give you a little bit of validation that maybe these pressure spikes are somewhat realistic. So then if I go on and I add my 30 sections in here, you can see very similar trends, but with 30 sections, look, I'm actually getting to even higher pressure spikes, even closer to 900 psia. So which is right, 900 or 700 or 850? Well, this is where you can use a different cavitation model to compare. So in my impulse model, that would be this family of scenarios. I've got a discrete gas cavity model, 10 sections, 20 sections, and 30 sections. So I already ran the results. I already put out the results into my spreadsheet, so I'm just going to go right to it. Here's my discrete gas cavity model results. As you can see, it looks slightly different than the vapor cavity model, and it's a lot more stable. As you can see here, the cavitation happens a lot less, where the pressure is actually at vapor pressure with the gas cavity model than the vapor cavity model. So when you look at this in more detail, if I go in here and I only look at one at a time, there's 10 sections, and then here's 30 sections. So those two situations compare fairly well with each other. Again, the discrete gas cavity model is a bit more, it's a bit more accurate. And as you can see, when you compare from 10 sections up to 30 sections, you're still getting around 850 for that maximum. So that is what you would probably design your pipe system, is to be able to withstand this level of pressure. But here's the thing. This is an instantaneous closure where the valve is closing in 1 millisecond. Those pressure spikes are very large, but they are not sustained for very long, and they happen very quickly. When you're evaluating your cavitation, one of the things that you want to see, or when you're looking at your results, is if you see a spike that goes way up in one time step and back down in the other time step, that may not be realistic. What you're looking for is multiple solutions. So if you have a time step where it increases to here and then it increases a bit more and then it rises, if you see a progressive increase in pressure over time and then it drops down in the same fashion, this is what would tend to show if that pressure spike is more realistic or not. So that's another thing to look for, is when you're evaluating, does it go up and down in one time step, or does it take a few time steps to increase and then decreasing? And when you increase your level of sectioning, that's where you can get more resolution there. I'm not saying that you have to use 10 or 30 sections every single time at all. You might only need to do one section or two sections. It depends on how short your controlling pipe is. In my model, the only pipe I have is 2,000 feet long. So 30 sections, still does not have a very short pipe length. And so that's how I'm able to use a 30 section in my model and get away with it without having a extremely long runtime. Now, you don't want to close the valve in 1 millisecond. And so this is where I created my other scenarios, where I did a 1 second closure and a 2 second closure. The overall goal when you're doing your transient analysis with Impulse is to figure out how to not cavitate. That's the key thing here, is not just how do you understand cavitation. The whole idea is how do you eliminate cavitation, or how do you reduce the level of cavitation? Well, if I take a little bit longer to close the valve, that will help potentially dampen out the pressure spikes that you might see. So that's where I had my other scenarios. So if we look at the discrete vapor cavity model for a 1 second closure, this is the resulting transient response. You can see here that the cavitation is starting to become a little bit less. It still cavitates, but not as much as it did before. Here, you can see how the maximum pressures are falling in line a lot more with what Joukowsky is originally predicting. So these may be fairly realistic, especially because of how when I use different amounts of sectioning, you can see how the pressure values rise up to that value over several time steps. If you do a comparison with the discrete gas cavity model, it's similar. Again, gas cavity model, less noise. But again, you're still cavitating. The goal is don't cavitate. Well, here's my 2 second closure case. As you can see, with closing the valve in 2 seconds, no cavitation. And so you have much more smoother results. I actually am plotting all 3 series of data at the same time, and they're exactly overlapping each other. That's because there's no cavitation, so the results should be the same, if not extremely similar. The gas cavity model shows the same behavior. So when you don't have any cavitation, it's a lot easier to predict what's actually going on in that system there. All right. Again, if you email me, benkeyser@aft.com, when I send you a zip folder, I'm going to give you this model with all my scenarios as well as my spreadsheet. So you'll have all that data there. All right, where was I? Moral of the story is don't cavitate. There are a lot of ways to prevent cavitation, allow for longer periods of time for things to happen, longer valve closure times, change the way things change over time. So instead of closing the valve linearly, maybe do the 80-20 rule. That's the webinar that I did in the middle of October, surge mitigation. That's where I talk about the 80-20 rule a lot. Consider designs with larger pipe diameters to avoid steady-state velocities. That can help reduce your surge pressures. Incorporate surge suppression equipment like gas accumulators or surge tanks. But if you do cavitate, the reasons for the difficulties, as well as tips on how to identify cavitation when it's not obvious, is what I'm going to talk about next. So these are the difficulties for cavitation. In reality, your cavitation of your fluid, or the wave speed of your fluid, changes when cavitation is present. For the 2 cavitation models in Impulse, we're assuming a constant wave speed. Even though the gas cavity model can mimic a variable wave speed, it's still assuming that it's constant. So it gives you the I can't think of the right word. It gives you the appearance of a variable wave speed, and that's why it handles the cavitation better. The other assumption that's important to pay attention to is all vaporization is located at the computing stations. So if you have a pipe that's broken up into bits and you start to see a vapor bubble form right here, in the model, that vapor bubble is going to stay right there. In reality, that vapor bubble can grow to be larger and larger and larger, and Impulse is not going to show your bubble necessarily growing, and also it's not going to be able to move. So if you have a sloping pipe, in reality, there's potential for the vapor bubbles to travel. In Impulse, they're going to stay at the computation stations. So those are very robust assumptions that make cavitation modeling very much less certain than liquid modeling. As you saw in that 2-second closure case, the results were exactly right on. Because there's no cavitation, it was a lot easier to predict what the actual phenomenon will be. When using the discrete vapor cavity model, these are important concepts to keep in mind. Also keep them in mind for the gas cavity model as well. The first 1 or 2 or maybe 3 pressure spikes after cavity collapse are going to be the most reliable. After you start to cavitate more and more and you have more and more pressure spikes, that's when you start to see the non-realistic, chaotic behavior start to happen. Some of them may be real, but a lot of them may not be, so you have to look at things carefully. Pay attention to the maximum vapor volumes in relation to the section volume. Rule of thumb is, again, if that vapor volume is 10% of your section volume or less, your resulting pressure spikes will be a bit more reliable. Now, does that mean that once it goes above 10% that it's not reliable? Not necessarily. That's where you have to look at everything together. Focus on the major trends of pressure results. Again, if you just see an isolated spike that comes up and down in a single time step, that may not be realistic in comparison if you see a progressive increase in pressure over several time steps. That would be more realistic. Some more difficulties: if you start to have persistent cavitation, it can result in unrealistic results. The mathematical limitations become more important, and so cavitation is a two-phase flow problem, which can only be approximated by very sophisticated mathematical models. So it's not an impulse issue, it's a mathematical model issue. And so the discrete gas cavity, discrete vapor cavity models, they do not model true two-phase flow behavior. That's why they're only very good when you first start to cavitate, or you have at least short-lived spurts of cavitation. There are two common situations where cavitation can happen in impulse models, either in the initial steady state or in the final steady state. And the final steady state of the system is essentially after your transient phenomenon, it results in cavitation for a very long period of time. So let's look at these two cases. Here's a simulation where we have cavitation in the initial steady state. And this is very similar to how AFT Fathom would identify cavitation. What it does is it compares the static pressure at each of the points in the pipe with the vapor pressure. And if the static pressure is less than the vapor pressure, you're going to see a warning message that will not allow your model to be able to run. Well, here in this model, we have a high point at 90 feet, and our transient is very simple. We're starting off in the steady state, going from 200 gallons per minute to 400 gallons per minute in 5 seconds. Why is the system cavitating? We're going to actually look at, well, I don't have time. I was going to show a Fathom model, but let me open up the impulse model here. All right, 1 second. Okay. So here's my my model with the initial steady state. And as you can see, for the transients, I'm going from 200 gallons per minute to 400 gallons per minute. Well, I am doing a transient simulation here, so when I turn on the transient mode, I'm going to try and run my model in 30 seconds. And so when you run your model, immediately it's going to throw up this message. It says, error occurred while running solver. Cavitation exists in steady flow results. Transient calculation cannot be performed. So this means that your steady state initial condition is already cavitating. The results will not be predictable with AFT Fathom. It will only be able to tell you where you're cavitating. So let's do this. In Impulse, you can switch to a steady state only mode, and you could rerun your model in steady state, and you can actually see exactly where you're cavitating. So here, this tells me that my static pressure is lower than my vapor pressure at the outlet of pipe 3 and the inlet of pipe 4. So where is that in my model? Well, it's right here at the high point. So here's pipe 3, here's pipe 4. At the high point, I'm cavitating. Well, why am I cavitating? The system pressure is negative 11 psia. Well, mathematically, Fathom and Impulse in steady state mode can calculate a negative absolute pressure. Not real, so these results would not necessarily be realistic. They may be garbage, but it's telling you where you have a problem, and you have to fix that problem. Different ways that you can fix that issue in order to get, the goal is to eliminate cavitation in steady state. Well, if you can make this elevation be lower, then you can be able to pump over the hill a bit more effectively. Now, here's what I did to really physically understand what's going on here. Is I took this model and I opened it in AFT Fathom. And so that's the beauty of our products, is that when you know one of the softwares, you know the others, and you can also take a model from Impulse into Fathom, or you can take a model from Fathom into Impulse. So when I brought it into Fathom, I used the pump sizing capability to find a pump curve for the pump. Then I actually replaced this branch with a control valve in my Fathom model. The reason why is because I wanted to be able to generate a pump curve and a system curve. And so when I was able to get my pump curve here, it plotted the pump curve as the regular system would. Here's my 400 gallons per minute. That's the final state where it can pump. But at 200 gallons per minute, it can't. Well, what's going on here? If I was to put a pump curve in there at 200 gallons per minute, this is the system resistance that the pump needs to be able to overcome, which, as you can see from the pump curve at that flow rate, it certainly does. But the problem is, if you put a control valve in there, in order to get this flow, your control valve has to take out this pressure loss. So when you have a large pressure loss across your control valve, the pressure available to get up the hill starts to cavitate. And so that's what I did to be able to really show why you're not able to pump at 200 gallons per minute. So keep that in mind, is if you're not able to get the transient running because you're cavitating in steady state, you have to find a way to be able to eliminate that cavitation there. And so that's an effective way to be able to look at it. The other situation is if you are cavitating in the final steady state. Just so everyone knows, I've got about 2 minutes until the hour, and I've got probably about 5 to 10 more minutes of content here that I want to show. And so if you need to head out, thank you very much for listening in. You will receive a link of the recorded webinar. That way, when you get that link to the recording, you can zoom ahead to 58 minutes and then watch the last 10 minutes or so. But if you want to stay online with me, feel free to do so, and I'll finish up here shortly. So thank you all for your time. All right, so marching forward here, if you are cavitating in a final steady state, it's a bit more difficult to identify. So the results can be a lot more dramatic. So here, instead of going from 200 gallons per minute to 400, I'm going to do the reverse. I'm starting at 400 GPM, going down to 200 GPM. And what you'll find here is that you actually have a very concerning critical warning message. It's telling you that your pipes have vapor volumes in their stations greater than 100% of the liquid computing volume. So they are getting very large. Well, what's going on there? Let's take a look. So here's this scenario. And again, my pump is starting at 400 gallons per minute, dropping down to 200 gallons per minute. So when I run that, I forgot that I already had results. Here's what we're going to see, is we're going to see a plot where we're going to look at the pressure at that high point as well as the vapor volume. Okay, so I've got my results. Here's my two warning messages telling me that I have massive amounts of vapor volume. Here's what's going on, is if I plot the pressure at the outlet of pipe 3 as well as the vapor volume, this gives you a very clear indication as to what's going on. When you cavitate at that 200 gallon per minute time, your pressure drops to vapor pressure and it stays there. And this vapor volume tells you that your pipes are continually filling up with air. Well, what's really happening there? What's really happening is, in reality, your pipes are going to drain. And so in reality, when that vapor volume is filling up more and more and more, in reality, your pipes are going to drain and your system is going to just be sucking in air constantly. There is a way that you can get close to approximating an idea of what this behavior would look like. What I have done is I've created this scenario where I used a vacuum breaker valve junction, and this is going to be a valve that pops open when pressure at that high point drops below my atmospheric pressure, and it'll allow air into my system. Well, when you use a vacuum breaker valve, you can do a special modeling feature in a pipe, which is called a partially full pipe feature. And so if you turn this on the optional tab, this can give you an indication of how long it would take, perhaps, for your pipe to drain. Now, once that pipe drains, the results are not accurate anymore. But it gives you an indication where you can see how much air comes in through the vacuum breaker valve, and you can see how long it takes for that volume of liquid in your pipe to drain over time. Now, there are some very special caveats to using that partially full pipe pressure feature carefully. So make sure that you read the help file that talks about how to use the partially full pipe capability. We also have a blog article on it that you can find on our website that gives you some tips. But that's what's happening there, is if you're starting at 400 gallons per minute and you're dropping the flow down to 200, essentially that pressure is not able to maintain above vapor pressure, and in reality, your pipes will be draining. So that's where Impulse starts to deviate from reality a little bit. But if you look at how I'm in the wrong scenario. If you look at how the vapor volume of that graph that I did, if it, let me regenerate it here really quick. If you see something like this, where your vapor volume goes up and up and up, this is sustained cavitation. That's not going to give you realistic results. That means you have a major issue, and so you might want to do a pump trip and then see how your valves close and whatnot. And so this is where you have cavitation in the final steady state, and this is how you can identify where that's happening and why that's an issue. All right, last example. So here we have a large system, and my transient is to close this valve over this profile. The valve is closing in 30 seconds. And I know that I'm going to have cavitation in the system because I already looked at the results. And essentially, you're cavitating down in the flow path in that area right there. And so this is the same type of results that we're looking at. We have a warning message that tells us our vapor volumes are growing to be much larger than the section volume in a certain pipe. Well, that pipe is pipe 73. So this is a plot of how the vapor volume grows over time at that single pipe station. And here you can see the resulting pressure spikes that you would see when the vapor bubbles collapse. So when you see the vapor bubbles collapse, that's when you're going to see a pressure spike at the same time. So when you look at those things together, that will help you figure out what's going on a lot more effectively. So in this particular model, again, when you email me, I'll send you the model, and that way you can look at it yourself. The pipes 71 through 78 start to have persistent levels of cavitation. So you can plot the static pressure and the vapor volume at pipe 73. And if you look at that vapor volume here, the section volume of pipe 73 is about 21 cubic feet. Well, when you look at this here, those vapor volumes are clearly larger than 10% of your section volume. The pressure spikes may not be realistic. Well, how do you know? Well, if I go into Impulse and I open up that model file really quick, Oh, that is unfortunate. For some reason, I thought that I had output data, but it doesn't, and so this model actually takes a bit of time to run. So I'm not going to do that here. But essentially, what you would start to see is this transient response here that I already plotted in the screenshot. But the key thing is, when you're evaluating your results, don't just look at one single pipe station. That's not going to give you an indication of the whole story. In this model here, where's pipe 73? It's right there. It's between these two junctions. That's where you have the largest amounts of cavitation, and your valve closes right here. So this is a situation where your valve closes way here, but your cavitation happens much further away in your system. It's happening in this area of the model. Well, what's going on is you have some elevation changes in those areas, and when your elevation goes up to some high points, that's your elevation, your pressure is going to decrease. So when your valve starts closing and this starts to shift downwards, this pressure, which is located right here, that drops to vapor volume. So you don't want to look at only the outlet of pipe 73. You might want to do an animation. And so if you did an animation, you might select all the pipes in this continuous flow path, and you would use the animation capability to look at maybe both pressure and vapor volume, and you would see how the pressure and vapor volume in that flow path over length animates over time. And you can zoom into these areas on that graph, and you can see when things start cavitating, and that will give you an indication of what's going on in your system. How do you know if those pressure spikes are real? Well, just do the same type of analysis that I recommended. Is one thing, switch from using the discrete vapor cavity model to the gas cavity model. If you switch to the gas cavity model, and if you see very similar trends to the magnitudes of vapor volumes, as well as the magnitudes and timings of those pressure spikes, then that may mean that they might be a little bit more realistic. Now, in this particular model here that I'm using, my sectioning is a bit different. So here, my controlling pipe is pipe 13. Pipe 13 is 7.3 feet long. Well, in 7.3 feet long, I'm actually using 3 pipe sections. That's a lot of sections. That's why the model takes so long to run. So if you use 1 section, or maybe 2, or maybe 4, and you see the same types of trends and results in both cavitation models that you're seeing here, well, maybe these magnitudes might have a level of being realistic. But again, you're only going from 20 psia to 40 psia for the maximum values, so that may not be incredibly severe. Your piping system might be able to handle that. So that's how you can evaluate that in a bit more detail. Again, if you go to our Impulse help file that I showed you, there are some additional pieces of guidance that you can read on how to evaluate your cavitation results a bit more effectively. I showed you the basics here, and then you can also read those 2 technical papers. That gives you a lot more general guidelines on what you can do. Last but not least, we have what's called the AFT Flow Expert package. And so this is an excellent package, which is really just a block of consulting hours that you can buy off the shelf. So when you need some extra help, especially when you're dealing with AFT Impulse, if you have cavitating behavior, again, step 1, figure out how to not cavitate. If you can figure out how to not cavitate, or at least reduce the level of cavitation, it's a lot easier to box in your answer more effectively. But if you keep having cavitation and you need some more assistance or some more ideas on how to avoid cavitation or how to understand your cavitation behavior, this is where you can purchase some off-the-shelf hours, and maybe you just need 5 hours. So you give us a call. Hey, I've got some really odd cavitating behavior in my model, and I need some assistance understanding it. Can you help me get a better determination if these pressure spikes I'm seeing are more realistic or not? Well, with the Flow Expert package, we can go beyond the scope of tech support by actually understanding your physical system at a more detailed level, and that's how we're able to provide a little bit more guidance on which spikes might be more realistic, which ones may not be. So that is something that you can find information about on our website. We also list our prices for the Flow Expert package, and you can find that on the webpage as well. Okay, everyone, thank you all very much for your time. One of the fundamental things that I would highly recommend for AFT Impulse is training. Fathom and Arrow, our steady state tools, are really easy and intuitive to use, especially with the interfaces. The interface of Impulse itself is also very easy to work with, but the thing is, waterhammer is a much more difficult beast, and it's a lot more likely to where you would use a tool like AFT Impulse in an improper way than you would for the steady state tools, which are easier to work with. And so that's why we highly recommend you have the appropriate level of training in order to use AFT Impulse effectively. So we have training seminars at our facility in Colorado Springs. On our website, we already have the training dates for 2019 posted. That way you can come to our facility, or you can have us come out and train your team at your site. If you're interested in that, you can contact me and I can get you a quote for us to come and do a on-site training seminar. Impulse is a 3-day training class. It's very important to be able to go through that if you really want to understand how to use AFT Impulse effectively. If you're not able to come to training right away or have us have to train you and your project is now, then that's why I recommend the AFT Flow Expert package. We can walk with you as you start to get up to speed on how to do those types of analyses. Thank you all very much for your time today, and I appreciate those of you listening in. And if you have any questions, don't hesitate to contact us. My phone number, or you can find our phone number here. And again, email me directly, and I'll send you the model files as well as the presentation slides. Take care, everyone. Have a wonderful day and a Merry Christmas and Happy New Year's.